We've been studying sinusoidal frequency response for a little while now, including a bunch of material with Bode plots and whatnot that'll be on your exam, right? And I talked last time some about how using our Fourier series analysis, we can understand a signal that's not a sinusoid as being composed of a bunch of sinusoids, right? If it's periodic, you can write a series of sinusoids that are summed together that represent the signal. So, like I said last time, you can use the idea of superposition to apply all that we learned about frequency response functions, not only to sinusoidal input responses, but any sort of periodic input responses, which makes all that frequency response function stuff way more powerful than it would be otherwise. Okay? So, we're just going to kind of tie all of that discussion in a bow today. And I hope that the high-level understanding really comes through for you, because that's what I think is the most important aspect. So, let a system have this input, u of t. What is this? What is this? So it's a sum of a bunch of sinusoid terms with different phases and frequencies and amplitudes. What did we call that last lecture?
Steady state.
A Fourier series. Fourier series. Yeah. Well, it's going to be related to the steady state response in a moment. So, and we could also represent it with this imaginary exponential form as well, right? Which we talked about as well. The nth real harmonic is un. We'll just call it un. A is equal to an sine n omega naught t plus phi n. So I'm just taking one of these sum terms, or not just one of them, but a generic version of one of the sum terms, and writing it here as un, which yields the output. So if we just took one of those terms, we looked at what happens to the system if we put in just that one, right? So we have the sum of a bunch of them, but let's extract just one term from this input. And let's write what its response would be. This is a sinusoid, right? And so we know the steady state response for a sinusoidal input is, so I'm going to write yn of t. So the n means it's corresponding to this un input is equal to, do you guys remember what this would be? You guys remember the formula for it?
H omega j times sine of whatever.
So magnitude of h of j n omega naught, so you have to put in the frequency, times the input amplitude, which is script a n, right? So we scale the input amplitude by the magnitude of the frequency response function, okay? And then we have sine of n omega naught t is also the frequency, so n omega naught is also the frequency of the output, right? Frequency doesn't change. The original phase is still in there, but then you add another phase to it, right? Yeah, so we could either call it psi, or I'll just write it as the phase, the angle of h of j n omega naught. So that is that totally jives with our understanding of what happens if you put a sinusoidal input in. You get a steady state response that is a sinusoidal output with a changed magnitude that's scaled by the magnitude of the frequency response function, and a changed phase that is summed with, the original phase is summed with the phase of the frequency response function. Okay? Now, applying the principle of superposition, so I'm essentially doing in a little slower mathematical, systematic way what we've talked about the last couple of weeks now, where we can use this idea of superposition and we can say, oh, okay, this is the output for this input, so we could write the output for any of these inputs, right? We could just take the nth one and write it, and therefore, using superposition, we know that if you sum up a bunch of inputs, you can just sum up a bunch of outputs that correspond to each input separately, right? So it's pretty great. Only applies to what type of systems? Nonlinear systems? Does it apply to those? Superposition? No. Doesn't work for nonlinear systems. It only works for linear systems. So y of t is equal to, so it is the DC term we haven't really talked about, but the DC term, you take the input, which is 1/2 a naught, and you scale it by h of j 0, okay? And this is the DC offset, we've called it, or the DC component of the frequency response function, when omega equals 0. And then plus all of these sinusoids, so we have to write another sum from n equals 1 to infinity of h of j n omega naught script a n sine of n omega naught t plus phi n, the input phase, plus the phase of the frequency response function, h of j n omega naught. So the sum of all of these y(n)s. I mean, I could have written this more compactly by just saying the sum of all of the y(n)s, but I wrote it out instead. Yeah?
The first a after the 1/2, the a naught and a n.
The first a after what?
After the 1/2.
Ah, yeah, that's a naught. Okay. Similarly, for inputs expressed as complex Fourier series, so we could represent the input as being this, right? This term, this expression. And that gives us an output for each term of, instead of having to take the magnitude and the phase separately, we can just multiply the complex number, which is nice. That means that there's complex multiplication here, but when we were working with the sinusoid, we were working with all the real numbers. The magnitude and the phase always come out to be real numbers. This is a complex function, so you have to multiply complex numbers together, so you're keeping track of it just in a different way, right?
What's that little pebble thing?
The pebble thing?
The little, yeah, what is that?
This one?
Yeah.
So that is, so un is the complex, this is capital U. So I try to differentiate my lowercase u's from my capital U's by making a big bar over them, just so it's easier to see. It's just the complex amplitude of the input.
I didn't know it was a U.
Yeah, I know, it is a little weird, but it's also like a tongue sticking out like that, out of a neutral face. Okay, so if you put in that complex amplitude, you get this out for each term. So if you wanted to write the entire thing, it comes out to be the sum from n equals negative infinity to positive infinity of h of j n omega naught times u, capital U, n e to the j n omega naught t. And this expression, I mean, it is kind of nice. It's simpler in a lot of ways, but it's not as intuitive. And that's why, even though mathematically working with a complex representation is easier, often we think in terms of the trigonometric representation because it's more intuitive, I think, to us. It's not obvious in this second boxed equation that we're simply summing up a bunch of scaled in amplitude and added in phase sinusoids. It is obvious in this expression, and that's why we tend to think in terms of this one, but in some cases we might find that this is actually easier to work with mathematically. Same exact quantities that are being dealt with, it's just a different representation. So let's, before we see the handout periodic input response, I want us to keep in mind, like I said, this is only valid for linear systems because superposition does not apply to nonlinear systems. So important to keep in mind. Periodic input response handout can be found on the website. Here we go. Okay. It is under the resources section. And this is, I'm not sure if it says on there. This is actually originally was written by Joe Garbini, Professor Joe Garbini at UW. I am sort of his protege, I guess. He was my advisor at UW, so that's why some of this stuff that I give to you as handouts is stuff that he made. So I thought that this was a really nice way of visualizing this, and this is what, this intuition we're trying to gain. This is how people think about it, is in these terms, in this sort of visual way. Oftentimes, a lot of engineers think in this way. So let's look at a magnitude and phase plot. So this is, if the magnitude is in dB, then this is a Bode plot, right? And if this omega is is logarithmically scaled. Although in this case, it's not. So we're just doing magnitude and phase plots linearly scaled. So this, we wouldn't probably call this a Bode plot, but it's representing the same thing that a Bode plot represents, right? So we have a magnitude and a phase of our input. So our input, we haven't actually thought about it in these terms before, but our input has a magnitude and a phase at different frequencies, right? So if we go back to our lecture notes, our input has a magnitude and a phase at different frequencies, all multiples, integer multiples of the fundamental frequency omega naught, right? So we could represent it on an axis similar to this. So at each omega value, so at each integer multiple of omega naught, we have an amplitude, so whatever the amplitude of the sine wave is at that term, and we have a phase. So we could draw what's called a line spectrum, which shows the amplitude and the phase at each point. Okay, it's not defined. Well, it's 0 for any omega in between, right? It's only has non-zero values of omega at those frequencies. So that's a line spectrum of the input. Now, we're going to put that input into a system, right? And the system has some frequency response function that has a magnitude and a phase, right? Okay. And then, so this is like what we would draw a Bode plot of and all of that, right? Okay, so there's our magnitude plot, here's our phase plot. Then we have an output. So the output also has a spectrum, a line spectrum, and that line spectrum is going to be composed of, so if I was to show where that is, that's this box, right? The output is going to have a new magnitude and a new phase for each frequency. Okay? All it does is scale the magnitude and add to the phase. So, if we took an input magnitude and at omega naught, say, we would multiply that by the magnitude of the frequency response function and get out a new magnitude of the output, right, at that frequency. So that would be that point. If we did like the 6th fundamental frequency, we should do the phase first. So if the phase was, like, say, plus 90 there, I don't know what it was, let's say plus 90 there, it would add to this phase, which is a little bit negative, right? So it should drop a little bit to give ourselves a new phase. So say we went out to the 6th fundamental frequency, this magnitude and this phase, so the magnitude's right about there, and the phase is negative 90, let's say. The magnitude should be multiplied by something that makes it smaller, right? Assuming that this is 1, which it very likely is 1, this would end up being smaller, so it's going to shrink. And sure enough, this line spectrum point here is smaller after the 6th harmonic, and the phase is going to be, it was negative 90, and it's going to get even smaller, right? Because it's going to add to this negative phase, and it's going to get even more negative. Okay? So this is how we think of it in terms of being a filter. Okay? You have an input that's got this spectrum, line spectrum. You filter it through here, and what comes out is a filtered version of the input. So notice that the magnitudes around here, this looks like a resonance, doesn't it? So these should grow, the magnitudes around here should grow, and then out here, they should shrink out here, just get smaller. So sure enough, the magnitude of the input is larger here, and then they decrease as you get higher. So it's filtering out the higher frequency magnitudes. The phases add, so if you have a high frequency input phase that's at positive 90, it's going to go to something smaller than that, and then if it's already negative, it's going to get even more negative, right? So at high frequencies, we see that same behavior. So that's a way to think of this as being a filter, as sort of filtering the input line spectrum to create an output line spectrum. Okay? All right. Does that kind of make sense? No. Okay. Could you ask a question for clarification?
Like, this is what you got, this is what it goes through, and that's what you get it.
So as you increase so you're not increasing the input, or so you're increasing the input. So as you increase the input, the output is kind of gonna
So the input we're just going to say is whatever it is. So say it's some periodic function that you can write a Fourier series for. Okay? So we're going to say that it is what it is, and it has a, so we did a Fourier series analysis on it, say, and we computed what all of the ANs are. We computed what all of the phi n's are, and we're going to put that in. So this is our input. We know what all the ANs are. We know what all the phi n's are because we did a Fourier series analysis on it, and we plot them on this spectrum. So that's the first thing we do. The input has these magnitudes and these phases. So we're not going to do anything to the input after that. We just have the input.
Oh, so the ANs are on the y-axis.
Yeah.
Oh.
So these are the ANs. So this axis here is the amplitude of each of these sinusoids.
Oh.
And then these are the frequencies here. So at each multiple of the fundamental frequency, we have a sine wave there with a given magnitude, and we're just plotting all of them. And then what we're doing is we're filtering it. We're filtering this signal through the system. So it gets applied to the system, and the system has an effect on it, right? The effect is that it scales the input amplitudes by the magnitude, and it adds to the phase, the input phase, by the phase of the frequency response function. So that's what we've got represented here, the magnitude of the frequency response function and the phase. So if you feed this magnitude through, if you feed these amplitudes through this magnitude of the frequency response function, the stuff down here is going to be left alone, right? The stuff here is going to grow, because it's near that resonance there, it's going to grow, and the stuff out here is going to shrink. And we see that's exactly what happens. The stuff down here gets pretty much left alone. Then the stuff in here grows, and then the stuff out here shrinks. And then for the phase, it's just additive, right? We have this alternating plus and minus phase, so say plus and minus 90 degrees, for instance, phase. That's all going to shift by whatever the phase is. So down here, it's not going to shift much, but out here, it's going to shift down quite a bit. That's exactly what we see. We have the phase not being affected much up here, and then we're shifting down.
It's like it's going to go in the pattern of whatever the phase shift or the magnitude is. Okay.
That's right. So you're sort of like shaping, you can think of, I mean, and that's what designers do, system designers think of it in terms of like shaping this frequency response function so that the inputs that are coming in are either filtered out or maybe amplified depending on what they want at a given frequency. Yeah. Yeah, and so you're going to have some homework on this from when you get back, and we'll continue talking about this after spring break, but I did want to get to this point where we like sort of like saw the whole picture. Is there a question?
Yeah, so when you go back to your input magnitude, is there a reason why the 5 omega naught it dips down at that point and then goes back up at 6 omega naught?
This was just, I actually don't know what function he used, but that's not uncommon. It is usually the case that your amplitudes decrease as you increase in frequency.
Yeah, and then it hits a certain frequency and it peaks, but then it can kind of damper itself back out.
Yeah, so usually when you go to high frequency, it'll eventually go to, approach zero. But you have, it's not uncommon for it to dip and then increase. It just depends on the shape of the function. So this might be, and I don't know, this might be some sort of sawtooth function. As long as it's periodic, you can represent it with these spectra like this, with a Fourier series. So I wish I knew off the top of my head what it was. I don't recognize it, but yeah, it could. And it could be something just arbitrary, just made up, not something that we often think about. But if you have any weird, you could draw any sort of squiggle, and if you repeat that squiggle, then you have a periodic function, and you could write a Fourier series.
Trying to grasp like why that would happen. But.
Yeah. I wish I had a good way to give you some intuition on it. I don't. But I would like to know. I could ask him too. I still work with him on research, so I could ask him what function he used. Okay. Any other questions? I want you guys. I want us to make sure we take our time on this and understand it. So, are there any other questions on this material? All right. So,